Welcome to this explainer. All right, let's jump right in. Today, we're taking the ultimate upward journey through the invisible, multi-layered shield that completely surrounds and protects our planet. We're going to break down exactly how this incredible structure works, layer by layer. But to hook you right from the start, let me ask you this. Where does Earth actually end? And where does outer space officially begin? It sounds like a pretty simple question, right? Well, to find the answer, we can't just draw a single line in the sky. We actually have to travel up through a highly structured, 6,200-mile-high atmospheric envelope. Honestly, it helps to think of it like a massive multi-level skyscraper. So here's our flight plan for this explainer. First, the troposphere, the weather zone. Then, the stratosphere, the ozone shield. Third is the mesosphere, the coldest layer. Fourth, the thermosphere, heat and plasma. Fifth, the exosphere, the final frontier. And finally, we'll map the invisible boundaries. All right, Section 1, Troposphere, the weather zone. Starting right here on the ground floor, this layer extends up to about 12 miles high at the equator, but it's only 4 miles thick at the poles. And it is incredibly packed. I mean, the troposphere holds 75 to 80% of the entire atmosphere's mass and a staggering 99% of all its water vapor and aerosols. It's dense, it's turbulent, and because it's mostly heated from below by the Earth's surface soaking up solar energy, the temperature here drops pretty consistently by about 6.5 degrees Celsius for every single kilometer you go up. This steep temperature drop creates convection. Warm, moist air rises, expands, cools, and turns into clouds. Basically, this layer is the engine of all our global weather, and almost the whole shebang is trapped right here below a ceiling we call the tropopause. Moving right along to Section 2, Stratosphere, the ozone shield. This floor extends from the tropopause up to about 31 miles or 50 kilometers above us. Now, the absolutely crucial thing to grasp here is the dramatic thermal inversion between these two floors. You know how in the troposphere it gets colder the higher you go? Well, in the stratosphere, the temperature actually rises with altitude. No way, right? But it does. Why? Because of the ozone layer. Ozone molecules are busy absorbing high-energy ultraviolet radiation from the sun and converting that UV energy into heat. And since warmer, lighter air sits perfectly on top of cooler, denser air, this creates a highly stable, non-turbulent zone. That is exactly why commercial passenger jets love to cruise in the lower stratosphere. It guarantees a much smoother ride for all of us. But, that stability comes with a bit of a catch. This layer is extremely dry. And because there is essentially zero vertical convection or mixing, it acts like a giant trap. Stuff that gets pushed up here, like volcanic ash or those ozone-destroying chemicals we call CFCs, can literally linger around for months or even years. The only clouds you'll really ever spot here are rare polar stratospheric clouds. They're also known as nacreous clouds, and they only form over the winter poles when temperatures plunge below minus 78 degrees Celsius. Okay, Section 3, Mesosphere, the coldest layer. Punching right through the stratosphere and heading up to 53 miles high, we hit an absolute extreme, minus 120 degrees Celsius. The top of the mesosphere, known as the mesopause, is hands down the absolute coldest place in the entire Earth system. Unlike the layer right below it, the mesosphere completely lacks ozone to absorb UV heat. But it does have carbon dioxide molecules that efficiently radiate thermal energy straight out into space, causing the temperature to just drastically plummet. But don't let the cold fool you. The mesosphere is incredibly active. The air up here is thin. I'm talking atmospheric pressure that's less than 1% of what it is down at sea level, but it's just thick enough to act as a massive frictional shield. This is exactly where most meteors burn up as they hurtle toward Earth, and that meteor ablation leaves behind meteoric dust. The extremely scarce water vapor in this freezing layer actually condenses onto that space dust, forming noctilucent, or night-shining clouds, which are literally the highest clouds on Earth. This layer is also home to some truly bizarre high-altitude electrical lighting. I'm talking about transient luminous events known as sprites and elves that flash far above standard thunderclouds. Next up, Section 4, Thermosphere, heat and plasma. So, riding our elevator past the mesopause and going all the way up to 600 miles high, you need to prepare for some serious thermal whiplash. In the thermosphere, the temperature completely reverses trend again, skyrocketing up to 2,000 degrees Celsius. The highly rarefied molecules here absorb extreme solar X-rays and ultraviolet radiation. But here is the really fascinating twist. If you could somehow stand outside in the thermosphere, it would actually feel freezing cold to your skin. I know, that sounds crazy, but the heat just represents the kinetic energy of the molecules. The air density is so incredibly low up there that there simply aren't enough molecules colliding with you to actually transfer that heat. Now, within parts of the upper Mesosphere and Thermosphere, there's this highly charged subregion called the Ionosphere. High-energy solar radiation basically knocks electrons loose from their atoms, creating a state of plasma. This whole region is structured into D, E, and F layers, and they are absolutely crucial because they interact with our global radio waves. During the day, the D layer actually absorbs AM radio signals, but the moment the sun sets, the D layer vanishes because the ions and electrons rapidly recombine back into neutral atoms in the dark. This allows radio waves to bounce right off the higher E and F layers, letting them travel thousands of kilometers across the globe. Section 5. Exosphere, the final frontier. Finally, we've arrived at the penthouse. This layer begins at a statistical boundary we call the exobase. The exosphere is what physicists call a collisionless zone. The air here is so unbelievably thin that gas molecules almost never bump into each other. Instead, these free-moving particles just arc through space on massive ballistic trajectories. And many of the lighter molecules, like hydrogen, actually achieve escape velocity and slowly leak right out into outer space. In fact, this leaking hydrogen forms what we call the geocorona, which is a vast, glowing cloud of atomic hydrogen that observations show extends halfway to the moon. Which brings us to Section 6, mapping the invisible boundaries. So now that we've climbed all the thermal layers, let's take a quick look at the chemical boundaries. At roughly 100 kilometers high lies a boundary called the tropopause. Below this line is the homosphere, where turbulent eddy diffusion, which is basically just the mechanical mixing of air by wind and weather, keeps gases like nitrogen and oxygen perfectly and uniformly mixed together. But above the tropopause, in the heterosphere, the air is so incredibly thin that turbulent mixing just completely stops. Instead, molecular diffusion takes over, which causes the atmospheric gases to neatly stratify by molecular weight. So you get heavier nitrogen settling at the bottom and lighter hydrogen floating at the very top. To summarize our massive elevator ride, our 5 distinct atmospheric layers feature flipping temperature trends and incredibly unique defining features. And notice how every single thermal layer is capped by a corresponding pause boundary: the tropopause, stratopause, mesopause, and thermopause. These represent the literal ceilings where the greatest changes in thermal profiles and atmospheric physics actually occur. But this brings us right back to our original question: where does space actually begin? Well, this centers entirely on the famous Kármán line debate. The international standard, which is set at 100 kilometers, is based on calculations by Theodore von Kármán. He basically proves that at this altitude, the air is so extremely thin that an aircraft would have to fly at orbital velocity just to generate enough aerodynamic lift to stay aloft. However, the US and NASA use an 80-kilometer standard instead. Why? Because astrophysicists point out that if a satellite's orbit drops below 80 kilometers, the atmospheric drag becomes so severe that orbital mechanics completely collapse, which obviously prevents the satellite from completing its orbit. And that leads us to a pretty fascinating final thought. We live our entire lives inside this incredible, perfectly structured, multi-layered shield that completely protects us from the harshness of outer space. But as we just learned in the exosphere, our atmosphere is constantly, gradually leaking hydrogen out into the solar wind. So I'll leave you with this to ponder. Given that slow, constant venting out into the cosmos, how long will our planetary bubble actually last? Thank you so much for joining me on this explainer, and keep looking up.